Last time we discussed average rate of change for a function on an interval. This was change in f divided by change in x, f of b minus f of a divided by b minus a. And I mentioned this is the slope of the secant line that connects the point a comma f of a and b comma f of b. Okay, well, I also mentioned, for example, if you're driving down a straight road and you look at your speedometer, say it says 50 miles per hour. This is not an average over an interval. Okay, this is a different notion of rate of change. This would be instantaneous. So it's a rate of change at a specific time, or if y is a function of x, this would be a rate of change at a specific x value. And this is what we want to discuss today. So today, what we want is instantaneous rate of change for a function at a specific x value. Okay, this is not over an interval, it's at a specific x value. It's instantaneous rate of change. Well, this is a very wonderful formula for average rate of change on an interval, but what happens if you try to use the formula? The average rate of change formula. Let's say from x equals a to x equals a, because you think, okay, I'm wanting instantaneous. So I'll just have the two endpoints be the same number. This is problematic because look, you get f of a minus f of a over a minus a. This quantity is 0 over 0, and this is undefined. So this is definitely not how we want to do it. This creates an issue. So this is not correct approach. Oh, not correct. But the notion of a secant line we definitely want to use. So let's go back to the secant line. Maybe I will go back to blue. And let's draw a picture. So what I want to do is look at the secant line. So let's let h be small. And let's consider the interval a to a plus h. Now I'll draw a picture and then I'm going to have to erase some stuff to continue. But my picture I can put here. So we have a function y equals f of x. We have some x value, and this is where I'm interested in the instantaneous rate of change at x equals a. Okay, this is what I'm trying to understand. Here is the point on the graph, a comma f of a, for example. Now h is small. Maybe here is a plus h. Okay? And here is the point on the graph, a plus h, comma, f of a plus h. Okay? Now, this is now an interval. I can calculate the average rate of change on that interval. Equivalently, I can draw the secant line between these 2 points and calculate the slope. So let me draw the secant line here. Okay. Okay, so we can, maybe I will write this over here, we can connect these 2 points with a line. So we want to find the slope of the secant line from a comma f of a to a plus h comma f of a plus h. The secant line, well, I should say connecting. Find the slope of the secant line connecting those 2 points. Now, you see it in the picture. The green is the secant line, and the slope of the secant line is the average rate of change on the interval from a to a plus h. So let's write this out. The slope of the secant line connecting a comma f of a and a plus h comma f of a plus h, okay? As I mentioned, this would be the average rate of change from a to a plus h, but we get f of a plus h minus f of a divided by a plus h minus a, and this simplifies just slightly over h. Okay, now this is a very important quantity. This, well, first of all, as I mentioned, this is the average rate of change for the function on the interval a to a plus h. But also this has a name. Maybe I will add another color. This is called the difference quotient. Difference quotient. Okay, now what makes sense in terms of a definition of instantaneous rate of change? We are going to take h very, very, very small. So in effect, you're letting this black point get closer and closer to this other black point. We are going to have the interval will get very, 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 very small. Okay, but don't actually let h equal 0, because as we saw, well, when h equals 0, this difference quotient is undefined. But for h very, very, very small, this is how we will calculate the instantaneous rate of change. So let me write this in maybe blue. The idea. For h very small, this will be very close to the instantaneous rate of change of the function at x equals a. Okay? Now, let's look at an example. Here is an example. We have a student throws a book straight up. Okay? Don't try this at home. But you have a book. It starts, for example, the initial position, just evaluate, 0, 0, 5 feet. So you're starting, okay, about right here. Throwing it straight up. According to this position function, this is motion along a line. And this is how many feet in t seconds. Very nice. The question, what is the instantaneous velocity at t equals 1, question mark. Okay, this is a very nice question. It says, right, in that moment, t equals 1, what is the instantaneous rate of change? And the word velocity is important because if the book is traveling up, the velocity will be positive. If the book is coming back down, the velocity will be negative. Well, how can we start this? We can start this by looking at the difference quotient. So we want to consider the following, which would be, well, we would take the interval 1 to 1 plus h, and we would look at p of 1 plus h minus p of 1 over h. This is the difference quotient, and it's also the average rate of change on the interval from 1 to 1 plus h. Okay, and this, for h very small, is going to give us an idea about what the instantaneous rate of change or the instantaneous velocity is in this example. What we are looking at here in red is graphed p of t. This is the position function I just had on the board, minus 16t squared plus 50t plus 5. And then the green is the secant line. Here it's between the point 1 comma p of 1 and 2 comma p of 2. Okay, then you see here m. Well, this is the slope of the secant line. This is the average rate of change. Here it's from t equals 1 to t equals 2. But this m is the difference quotient, or the value of the difference quotient. Okay? Now, the question, what's the instantaneous rate of change? Or in this case, because we're working with a position function, it would be instantaneous velocity at t equals 1. We want to let this h, which right now it has value 1, get very, very, very small, very, very close to 0, and we see what is the value of the difference quotient approach. So let's go ahead and start doing that. Here you see, let's go to, very close, a half. Here's h is a half, and we have moved from slope 2 to slope 10, for example. And you can see this green line is now steeper than it was before when h was 1. Okay, so what this says, the average rate of change between 1 and 1.5 is 10. Okay, but now let us decrease h more. Maybe I will just type. If we did, let's say 0.2. Well, now we see the average rate of change 14.8. We did 0.1. We see 16.4, 0.01, 17.84. You see? And now 17.984, 17.9984. Let's do one more, okay? So now this h is, okay, there's 4 zeros and then a 1. Now, at least how it's graphed, it shows 139, 139, but they're not really the same point. One of the points, the blue point, the x value is 1.00001, like this. Okay, but just from our evaluating this difference quotient with some very small h, we see it appears that the instantaneous velocity at t equals 1 is, well, 18, and this would be feet per second. The answer is 18 feet per second. Okay, now we will come back to this example later today and actually calculate this 18 feet per second. Today is our Prelude to Instantaneous Rate of Change lesson, and I'm just going to talk about the idea of a limit for for a function of h as h goes to 0. Then in the next video, we will do more general limits and talk about properties of limits and calculating limits, things like this. But just here, let's state this for a function of h. So we have a function q of h, and this gets, I will say arbitrarily, close to a number L as h gets closer and closer to 0, then the limit, as h approaches 0 of q of h equals L. And this is written, it's a lot of words for what I'm going to write. It's written the limit as h approaches 0. Q of h equals L. Okay? This is the idea of a limit as h approaches 0 for a function q of h. What happens is h is getting closer and closer to 0. Okay? Then the function value is getting closer and closer to some number L. Okay, so then the definition of instantaneous rate of change for a function at an x value is a limit. It's a limit as h goes to 0 of, well, this difference quotient. So this would be f of a plus h minus f of a over h. This difference quotient is a function of h. Okay, then we take a limit as h goes to 0. And this is the exact idea that we just saw in that Desmos calculation. This is the slope of the secant line, or the average rate of change from a to a plus h, and then we let h get closer and closer to 0. Now, what is this? So this is also what's called the derivative of f of x at x equals a, and this is denoted f prime of a. This is something we will see a lot further. Well, this is if, so this means that if this happens to get closer and closer to this number, so this is provided that this quantity actually approaches some number, but these technicalities, I will just say we will come back to. Today's the prelude to instantaneous rate of change day. So we define it this way. We want to find the instantaneous rate of change for f of x is 1 over x at x equals -1. And I have sketched a graph of this function, and we see the point on the graph is -1, -1. Okay, well, first of all, what is this instantaneous rate of change? This is what we were just talking about. We want a limit as h goes to 0 of f of -1 plus h minus f of -1 divided by h. This is the difference quotient. Equivalently, it's the slope of the secant line on the interval -1 to -1 plus h. Now, I'm going to first, before I work with this, let's say generally with h, I'm going to first think about making a table which parallels the discussion we did in Desmos, gives us an idea of what the limit should be. So let's use a table. what I'm going to do is I'm going to have the change in x. I'm going to have the change in f, and then I'll take the quotient. And the change in x, this is just h, right? So let's do h equals 0.1. Let's do h equals 0.01, and we will do like this. And this will be enough in this example to get the idea. Let's compute change in f, and then I will divide. Okay, so what do I need here? I need f of minus 1 plus 0.1 minus f of minus 1. I need f of minus 1 plus 0.01 minus f of minus 1. And I need f of minus 1 plus 0.001 minus f of minus 1. Okay, so this is f of minus 0.9, which is minus 1 over 0.9. And then this is plus 1. So if you think about it, this is negative 1 over 9/10. Invert multiply. This is negative 10 over 9 plus 1. We get negative 1 over 9. Okay, so this one is negative 0.11 repeated. Here we have minus 1 over 0.99 plus 1. Again, this is 100, negative 100 over 99 plus 1. We get, I'll write it this way, over 99. And for this one, this is negative 1 over 999, oops, with a point, plus 1. This is 999 over 1,000. We invert multiply. We're going to get negative 1 over 999. Well, this one I can divide by 0.1 in my mind. It is going to move the decimal this way, and that's repeated. And for these two, I have minus 1.01 minus 1.001. Okay, I believe this is correct. Now, what does it appear, right? And I didn't keep going with smaller and smaller h, but it seems that, that the instantaneous rate of change at x equals negative 1 is negative 1, right? Just by looking at these three values. Now, let's find a way to do this more rigorously or accurately, where we're not only looking at three values of h. So how are we going to calculate this limit? Well, we cannot just plug in h equals 0, right? This is the whole problem to begin with, because we get 0 over 0 and this is undefined. But what we can do, so what we want to do is, let's evaluate the numerator. This is the change in f, and simplify. So I will add that, and simplify. Okay? And then, once we simplify this, we will divide by h, and then we will just plug in h equals 0. Okay, so let's first do this. Let's evaluate and simplify this quantity. What is this? Here we go. We have 1 over minus 1 plus h minus 1 over minus 1. This is minus, 1 over minus 1 plus h plus 1. Now, let's simplify this, meaning let's get a common denominator and add. The common denominator is minus 1 plus h. And when I add, what do I get? H over minus 1 plus h. Now this is looking really nice because what do I need to do in this difference quotient? This is my numerator. Then I divide by h. And now you see, because I have this written as a single fraction, I will be able to cancel some things. So now, first this and then this, f of minus 1 plus h minus f of minus 1 divided by h is h over minus 1 plus h divided by h. Right? Look, you might get confused because we have fraction over fraction, but really it's like this. And we could invert multiply, which maybe I'll write it this way. This would be h over minus 1 plus h. And the h is here. Right? Now you can cancel. This is 1 over minus 1 plus h. If this was handed to you and you're asked, well, what happens when h gets very, very small, very, very close to 0? Well, just substitute h equals 0. And you see minus 1. So through this simplification, we can now evaluate the limit. So now, the instantaneous rate of change of f of x at x equals minus 1, we know it's a limit as h goes to 0 of f of minus 1 plus h minus f of minus 1 over h. But we have simplified this difference quotient to 1 over minus 1 plus h. Now there's no problem, as I mentioned, with substituting h equals 0. So let's do that. Let's just, plug in h equals 0. We get 1 over minus 1, which is negative 1. Okay? And this we have actually calculated. This is the limit. This is the instantaneous rate of change, and it matches with what it appeared to be by making the table and evaluating a few small h values. Now I want to define the derivative, which is, we're going to spend a lot of time on derivatives, and in fact this is most of the focus of this course. But the derivative of a function is, it's a function and it's a limit as h goes to 0, f of x plus h minus f of x over h. Now, I will put maybe in pink a parentheses, provided the limit exists. And I touched on this earlier today. Don't worry about this pink right now. Today is the Prelude 2 day, and we're going to, the next lesson, tomorrow's lesson, is really talking more about limits and properties and calculating. And then we're going to come back to this and have a whole nother day where we calculate more. Okay, so this is a function, and the nice thing is, evaluate the derivative at a. it gives you the instantaneous rate of change of your original function at x equals a, okay? So let's go back to p of t position, and this is for motion along a line, okay? It's how we started this semester, and I'm going back to it right now. If I take the derivative well, I know it's a limit as h goes to 0, p of t plus h minus p of t over h. This is the derivative. What is this? Well, if you think about this, if we evaluate this at some a value, it gives me the instantaneous rate of change at t equals a. Well, we know the instantaneous rate of change of a position function is instantaneous velocity. So this derivative is the velocity function. Velocity. Okay? So this is something we see today and will come up a lot this semester. You have a position function. Take the derivative. And we will learn a number of techniques coming so that we don't always use this limit definition. But you have a position function, motion along a line. Take the derivative. We have velocity. Well, what happens if you do this again? If you take the derivative of velocity, let's think about units, and this can help us out, right? Let's say we're in a car driving down a straight road, which has been my example more than one time. We know the units. Let's say we're in miles and hours. This would be miles per hour. We see it here. The numerator is in miles, denominator is in hours. Okay, so now we have miles per hour, or miles per hour squared. What has units like this? Well, also think about it from a physical standpoint. You are in your car, okay, going forward, say, and you're going 50 miles per hour, and then your velocity is changing. So you're either speeding up or slowing down. This is acceleration. This is acceleration. And the units are in miles per hour squared, or you might see feet per second squared if you are, for instance, throwing the book up in the air in feet and in seconds, which I will come back to that example. But this is a big concept, so wrap your brain around this. You start off with position, motion along a line. This here, instantaneous rate of change of the position. This is, and I will add the word, instantaneous velocity. Okay, and this, with this new language, it's the derivative of position gives us instantaneous velocity. Okay, then if you look at this formula, it says the instantaneous rate of change of the velocity. Okay? Let me erase this so I can add the word. This is instantaneous acceleration. And in this new language, it says the derivative of velocity is acceleration. Okay? But this, what we see in this formula, it's an instantaneous rate of change of velocity is acceleration. Instantaneous. Okay. Now, what I would like to do is go back to this example that we had earlier of throwing the book in the air, and let's calculate. Here we go. This is the exact same position function that we saw in Desmos. Now we should get, when I calculate v of t, the velocity, instantaneous, and I evaluate at t equals 1, I should get 18, right? Okay. Well, here we go. We know v of t. This is a limit as h approaches 0 of p of t plus h minus p of t divided by h. Okay, well, I'm going to proceed like I did when we had 1 over x, where first I work with the numerator, p of t plus h minus p of t. This is minus 16 t plus h squared minus 50 t plus h, plus 50, excuse me, plus 5. This is p of t plus h, and then I subtract p of t, which is minus 16 t squared plus 50t plus 5. Now again, I want to simplify this as much as I can, then I will divide by h. And this amounts to here, we first must multiply out. So t plus h squared is really t plus h, t plus h. We have a first, outer, inner, last, right? Make sure you don't just say it's t squared plus h squared, because that's not right. And that's a common mistake that I see. We have to actually multiply everything. So we have minus 16. Let's see, maybe I will back up. We have minus 16. We have t squared plus, there's an ht and another ht. And then we have an h squared. Then we have plus 50t plus 50h plus 5. Now let's distribute the minus sign. We have plus 16t squared minus 50t minus 5. Let's go ahead and multiply out this first part to one more step before I start simplifying. I have minus 16t squared. I have minus 32th. I have minus 16h squared. And then I can just recopy everything from above. 50t plus 50h plus 5 plus 16t squared minus 50t minus 5. Oh goodness, this looks almost intimidating until we start realizing that some terms add to 0. So let's mark those now. We have minus 16t squared. We have plus 16t squared. Wonderful. What else? We have plus 50t. We have minus 50t. Okay? And it looks like there's one more. We have plus 5. We have minus 5. And now there's nothing else that cancels here. But what I can do, what's left is 1, 2, 3 terms. All of them have an h. So let's factor this out. Minus 32t minus 16h plus 50. Okay? Now this is wonderful because remember, this is the numerator. So my next step was I divide by h. So if I want p of t plus h minus p of t divided by h, well, I have this simplified. When I divide by h, I'm left with just like this. How wonderful is this? Because now the velocity is a limit as h goes to 0 of minus 32t minus 16h plus 50. Okay, there's no problem substituting h equals 0 into this expression. We get something. We get minus 32t plus 50. This is the velocity as a function of t, instantaneous velocity, of course. This is the answer for the velocity as a function of time. So we have found the velocity v of t equals minus 32t plus 50. And the units here are feet per second. And now, just as a wonderful sanity check based on the work that we did earlier, what happens when you evaluate this? Maybe I'll do this in pink. If you evaluate this at t equals 1, we get minus 32 plus 50, which is 18. And that gives a happy face because this is what we saw in Desmos. Okay, now what's left to do? Well, now we have velocity. The instantaneous rate of change of velocity is the instantaneous acceleration, a of t. So let's calculate this now. This is instantaneous acceleration, and this one is going to be a little bit shorter, but we use this function which we have already calculated, and I will do it in the steps of before. First, I will write out v of t plus h minus v of t and simplify, and then I'll divide by h and take a limit. This is minus 32 t plus h plus 50 minus 32 t plus 50. This is much shorter to simplify. Minus 32t minus 32h plus 50 plus 32t minus 50. And we see some things cancel when we add minus 32t plus 32t adds to 0. Similarly, plus 50 minus 50 adds to 0, and you see we are left with minus 32h. So now I can take v of t plus h minus v of t over h. Well, if you divide, maybe I'll do it in 2 steps this time, although I don't necessarily need to, we get minus 32. Well, what happens when you take a limit as h goes to 0? Well, there's no h here. A of t is a limit as h goes to 0 of minus 32. It's just minus 32. It's constant for every h. So here is acceleration. This is in feet per second squared. And this is the end of this. We have constant acceleration of minus 32 feet per second squared.